Chapter 31, Section 8, Influenza. Now, influenza has been around a long time. Influenza has caused us a lot of problems. Yes, nowadays we know as that irritant, oh, somebody's home with the flu. That means they're going to be out for a week. Rare occurrences, somebody gets sick enough they have to go to the hospital. But there was a long time there that influenza was not only the severely debilitating infection disease that we know of now, but it had a high mortality rate. Got to remember, 1919, I believe it was, the Spanish flu outbreak, that pandemic that killed millions of people worldwide. And this was, before airplanes. So to travel around the world meant you were on a nice, slow ship. It's what a lot of people forget when they're comparing influenza to the COVIDs and stuff like now. Oh, it's not as bad as COVID is now. Yeah, but there also takes weeks to travel just around our country, as opposed to when we hop on a plane, I can be anywhere in the country in 6 hours. Anyways, influenza, single strand, negative sense, RNA virus. Has an envelope, so it's stealing part of our cytoplasmic membrane, and has little spikes coming off it known as glycoproteins. 3 different types, influenza A, B, C. These different types, remember they grouped based on severity, based on geographical location, based on a whole host of criteria that we're not going to worry about right now. Influenza A is the most important pathogen. I think then C's next, B's last, if I remember correctly. So here's the nucleocapsid, the proteins encapsulating the RNA, and then there's going to be some protein gel stuff, a matrix, and then finally the lipid bilayer, the envelope. The envelope, and you can see the little projections coming off, are the spike proteins. The spike proteins are where we're going to interact with the receptors on our surface. They're going to hijack a receptor to trigger the uptake. That's how the virus gets inside. Now, we classify the different influenzas, specifically influenza type A's. We go through and we classify them by what proteins are on the surface. You have 2 proteins on the surface, hemagglutinin, neuraminidase, H and N, or HANA, depending upon which textbooks, which primary literature you're reading. One's to get in, the other one is to get out. Cuts. One hijacks a receptor, the other cuts the proteins, allowing between the envelope and the cytoplasmic membrane, releasing the newly made virus, the newly made influenza virus from the host cell. Different types of H, different types of N's, and they've numbered them numerically. So if you read the textbooks, you read the primary literature, and they're talking about influenza, you'll see H, alphanumeric designation, H and N, and then H, a number, N, a number. H1N1, H1N7, and H7N1, okay? It's the 7th version of hemagglutinin they've identified, and it's the first neuraminidase that's been identified. Certain combinations, H1N1 versus the others, is more virulent, does more damage, more easily communicable, passed on, does more damage, cause a more severe disease. Others, not so much. H attaches and releases. And you see these. They're individual glycoproteins that have to form a trimer. Remember, trimer means 3 of them have to come together. Dimer means 2. Monomer means it's just 1. So the HA and the NA are HA is a trimer, NA is a tetramer. 1, 2, 3, 4. 4 proteins have to come together to form the complete neuraminidase. 1, 2, 3 proteins have to come together to form the complete hyaluronidase. Yeah. Sorry, couldn't think of the word. Here's the problem, though. The virus we isolate today was not the same virus that we isolated last year in patients. Not going to be the same when we isolate next year. Why? 2 things. First, antigenic drift. Second, antigenic shift. Drift is some minor changes. Okay? Minor changes. Still, the H protein, the N protein look pretty much identical. Slight change in amino acids. Got to remember, as far as our immune system concerns, there is no virus. What there is a small portion amino acid sequence, secondary or tertiary structure, small portion of a much larger protein on the surface of a much larger virus. Your B cells that make the antibodies, your T cells that kill the viral infected cells don't recognize the virus, don't recognize the protein, they just recognize that little sequence, the secondary or tertiary structure of the H or the N proteins. Antigenic drift says that that little sequence, whether it's 10 to 30 amino acids in length, 1 or 2 of the amino acids are going to change. Doesn't change much in the grand scheme. Yeah, it's still the H protein, still the N protein, still functions the same. But as far as your B cells are concerned, it's new. Got to relearn it. It's going to take 2 weeks. Antigenic shift, well, this is a major change. Remember, secondary structure is alpha helix, beta sheet. Tertiary is what are the sequences of alpha helices and beta sheets? Well, antigenic shift says, well, instead of alpha helix turn, beta sheet, what if alpha helix, we're going to switch up the turn a bit, alpha helix, switch up the turn, beta sheet. Or instead of alpha helix, sheet. Big changes. May make the virus more infective, may lower its infectivity, but it's something completely new. That could be a problem. Here is, a little representation of what the difference is between drift and shift. Drift is just small little changes. Shift, big. Boom, 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 boom. Drift and shift have major impacts on who gets infected and who doesn't. Antigenic shift, while it may make it more or less infective in us, could lead to changes in host species. What was bird flu because of an antigenic shift, big change, now can infect a pig. Whoa. Pigs already have their own flu. We call it the swine flu. Now you throw in, there's a certain strain of avian influenza that can now also hijack pig. Because I'll tell you right now, as you sat here, past few days, past few weeks, whatever, you've been exposed to bird flu. You've been exposed to probably some swine flu some way. but or some other animal flu. But because their proteins can't interact with our receptors, you never got infected. A big enough shift means that the H protein on the bird flu can now interact with receptors on a swine flu just enough to cause a low level of infection. Not this overwhelming infection like the swine flu would for a new pig that's never been exposed, but just enough. Pig also gets infected at the same time with human. Big shift. You now get this reassorted something new that everybody, all of us, can get infected with. It's what they think happens, or it's what they're claiming right now with COVID-19. Started off as bat, jumped to something else in one of the wet markets in Wuhan, China. It jumped something that was already infected with maybe a human virus, a human strain, because there's so many people there and it's constantly getting exposed. You get a mix, now you got something new. Don't know. We do know there's been quite a few outbreaks, pandemic level. Remember, outbreak means increased numbers in a given region, a city, a state, the southeast US, something like that. But it's still within the borders of the United States. Once it crosses borders, and now it's regions geographically, now we're talking pandemic. Jumps continents, pandemic. Different flus, H1N1, H5N1, different years. So when you go through and they tell you to get the flu vaccine, what they have done is a couple of years ago, epidemiologists have sat down and they have tracked who's getting sick, what strains, which ones are low-level numbers, which ones are high. High ones are going to burn out. It's those low-level ones that one of those is going to take over, and that's going to be the one that gets spread all over the place. So we need to make a vaccine for that one because for whatever reason, the vaccines we don't have long memory. Our immune systems do not have long memory when it comes to the flu, because if they did, well, then here's a vaccine that has all the H's, here's the vaccine that has all the N's, good luck, God bless, you'd never get sick again. Doesn't work that way. For whatever reason, we just cannot mount an immune response, a memory response that lasts more than a year. So that's why you have to go back every year, get the booster. Here's the new one. Well, anyways, as I said, they'll sit down and they'll think, okay, it's 2022. We think in 2025, this is going to be the one. They all come to an agreement, and then they send that out. And over the next year or so, the different pharmaceutical companies that specialize in vaccines will produce an H5N1 vaccine, because we think this is going to be the one in 2024, 2025, whatever. Well, it turns out their prognostication, their forecasting has never been right. Close, but never right. So, you say, go get your flu vaccine. It's never been the right one, but it's close enough a lot of the time that it does help, but they've never gotten it right. What we've noticed of our most recent pandemics, COVID-19 now, SARS back in the early noughts, few in between. High density, high interaction with humans and animals means a greater chance for the virus to jump zoonotically from animal to humans. And then because of the high density, you get it spread around, and then it gets spread out, which is why you look at the arrows. All roads do not lead to Rome. All roads lead to China. Even though it's a big, huge country, they have most of the population is all centered up and down the eastern seaboard, their eastern seaboard. Millions and millions of people in cramped space, small cities, basically shoulder to shoulder, you know. So that's where they start. I'm not going to go into a long thing here because it is not politically correct right now. Prevention, immunization helps, but it's not foolproof, not like the MMR that we talked about last section. And they're looking at surveillance. Okay, let's see what's coming. Hey guys, something's coming out, something's spreading, limit. That's why you'll see in many of the Asian countries, they wear masks all the time. They feel that limits their inhalation of the aerosols that somebody else has spewed forth. There are a few things on the market. Tamiflu is one of them. Tamiflu is great if you take it early on when you think, oh, I'm starting to get sick, I'm starting to feel a little fluish. Tamiflu, if I remember correctly, inhibits neuraminidase activity. Virus gets into one of your cells, hijacks, takes over, makes all the copies. As it's releasing, remember, it's tearing off a piece of the cytoplasmic membrane to be the envelope, but the proteins are still holding it together. It hasn't completely released. That's neuraminadese's job, to go through and cleave everything so it can be a clean release. Tamiflu stops that. Everything gets made, everything gets assembled, and as it's trying to bleb out, it can't cut, it can't release, it's stuck. Thus, it can't spread to new cells.